The last important overarching topic for us to cover on vector analysis or tensor analysis, this is taking derivatives, and also now we're going to talk about integrals of vectors and scalars in this real world case where things rotate like tensors, is the fundamental theorems. So we've already talked about this in class. There's the fundamental theorem of univariate calculus, which is that if you take the integral of a derivative, it is equal just to the function being differentiated, evaluated at the endpoints of the integral. And there's no tensors or anything here because this is a one-dimensional function depending on a single coordinate, time if you like. The derivative is a total derivative because it doesn't depend on anything other than time. And then this is just the endpoints of that particular integral. Okay, so now we have these new fancy differential operators, the gradient, the divergence, and the curl. Do they have a fundamental theorem? Yes, they all do. The gradient theorem looks an awful lot like the fundamental theorem, with the gradient playing the role of the derivative. But since the gradient is a vector derivative, and it has an x component, a y component, and a z component, we have to dot it into a little increment of distance. And then we get the function, which now the function is not a function of just one variable, but it's a function of a position, which is a vector, and the endpoints are also positions, which are vectors. So the gradient theorem says take the gradient everywhere in space, traverse on some trajectory from point A to point B, and you will find that the gradient integrated along that trajectory is the value at f of b minus the value of f of a. So if we follow this winding trajectory from A to B, we can imagine taking little length elements as we go, that's our dl, and we're going to be interested in calculating the gradient of FL. F is now a field that fills all of space all around here. I've drawn a couple of topographic lines to indicate where f of L is increasing here. And so we might be increasing as we go from A to B. And the point here is as we go along, we're taking the gradient of FL, which is always oriented across these topo lines from low to high, and dotting it into the increment as we go. And what this says is that the gradient of FL from A, integrated from A to B, is equal to the value of f at B minus the value of f at A. If you think of this in terms of height, this is a good analog for this. The gradient of the height of a mountain range is like the steepness. So if we sum up all the steepness as we walk along, we end up getting the total height difference from the top to the bottom, and the integral as we go. Okay, so that one is sort of is somewhat related to this, but you have to get the geometry of where this goes. And the cool thing about this is actually path independent. So once you've given me the gradient field, I could choose any path I like to get from A to B, and I still get the same answer. So I could have gone way out there and come over to B, and I still get the same answer. I could have gone way back this way and get to B, and I still get the same answer. That's not true of the integral of any vector field, but it's true of the integral of a gradient field, that its integral is path independent. Okay, what about the divergence theorem? So the divergence is the 3D divergence of a vector field, and so we can take a volume integral of that divergence, which is at every point in space. It's a scalar at every point in space, so we do the integral over a volume, and we can think of, traditionally these are always drawn in the shape of a potato. My potato is kind of a lumpy potato, but if we zoom in, what we're doing is taking a volume integral over this volume, and we're comparing it to the surface integral over the surface of that. That's what the divergence theorem says. And so if something is diverging from every point inside the volume, it's going to puncture through the surface. And so if we're paying attention to the line, to the puncture, the vector that's coming out of the surface, it should be related to how much it can diverge inside. That's the concept of the divergence theorem. And so it says take the divergence and integrate over the volume. That's equal to the closed area integral. This little circle means closed, and that means we can't leave out any part of the surface area to enclose that volume of the vector field that's being differentiated in the divergence, dotted into the normal, the outward normal direction. So if the vectors were aligned along the surface, this would be 0, but if they're punching out, this is a positive. If they're punching in, this is a negative, integrated over the surface, over a little element of surface here, but it's over the whole closed surface to get that circle in. That's the divergence theorem. And the divergence theorem, we're going to do a lot of examples in class because that's really important for fluid dynamics and all things fluid and liquid and just keeping track of how much stuff is going in and coming out of a particular volume. And then the last one is the curl theorem, which is really important for the fluid dynamical concepts of vorticity, sometimes called Stokes' theorem. And it relates the curl dotted into a normal direction over an area to a line integral of a closed surface, a closed circuit, I guess, around within this same area that bounds the area, a line integral in the same sense that we had a line integral for the gradient theorem. And here's the little piece of geometry to think about for that one. So here we have an area. Oops, not looking at the right thing. Here we have an area, and in the area I have drawn a little circulation pattern. So there's a curl popping out, the curl of u. This is u circulating around. That's the curl of u coming out. So if we take the curl of u, dotted it into the direction normal to this surface, and integrate over the area, that should be equal to u dot dl integrated around the periphery, like this. So this one, too, like the divergence theorem and the gradient theorem, has a kind of sense of path independence to it, which is once you give me that circuit around the edge, I can choose any area that's bounded by that circuit, and this function is still true. So I could have a nice flat one like I drew there, or I could have a kind of crazy balloon one that goes way out, but then still is bounded by that circuit around the edge, and you still get that the integral of the curl of the vector field dotted into the normal direction to that crazy new surface is equal to the circuit around it. All right, those are the three fundamental theorems of tensor analysis calculus. Those are really important for all kinds of things, fluid dynamics and geophysical.